Welcome to ILSTAR. In previous videos, we discussed our goals and tasks, pursuing to design a lunar racer that is able to travel as fast as possible around the landing site. Now it's time to show some progress.
According to the Terrestrial Study from Apollo 15 results, we acquired some information about properties of the soil mechanics at Hadley-Apennine region, the site traversed by lunar rover vehicle. NASA's report claimed that the soil was slightly cohesive and adhesive, granular, but the size of grain was very small. The sharpness of soil at that location was described as blocky angular and sometimes spherical. The astronauts also documented data on bulk density, fold ratio, and porosity from samples extracted by RV.
With some decent knowledge of lunar environment, we designed our racer's wheels and driving system, both of them are crucial contributors to racing. After several proposals discussed considering tire functions and dynamics, our current wheel design is very much like the one on LRV in terms of shape, but essentially they're very much different. With 14 cm in diameter and 4 cm wide, the narrow wheels are supposed to have a significant portion of itself sinking into lunar soil, which increases grip and stability, especially when the racer comes across crests or any potential jumps. The tires are covered with 24 spikes and 48 holes, both of them contribute to grip and tire sinking, while the holes can also cut away mass and decrease the moment of inertia as the wheels rotate, and it prevents lunar soil from piling up inside the tires. The tires are made of magnesium alloy to ensure elasticity and lightweight, and the rims are made of aluminium 7075 T6 to maintain the strength. Altogether, each wheel weighs just over 60 grams. To power the wheels, we proposed 4x4 and 6x6 layouts and discussed the necessity of gearboxes during online meetings. Due to weight and power limitation, we choose the 4x4 layout with a single motor powering each wheel. Considering the layout and on-spur mass, we need small motors with planetary gearboxes. So we picked the Navarrete 40 gear motor provided by Andy Mark. The average voltage transmitted will be lower than the 12-volt standard, but we've already looked online and proved the motors could operate under certain voltage. However, there are more problems coming.
Thermal control is difficult on the Moon during the lunar day. The main challenge is the absence of an atmosphere, which disallows the cooling through convection. As an alternative, we consider radiators that emit heat to space. We also use reflective material to minimize the heat gain from the incident solar flux. These two strategies maintain the thermal balance throughout the race.
From Earth to Moon, communication lag is too high for manual controls in a real-time manner, so an autopiloting system is necessary for both safety and agility consideration. Our potential challenge is to design an algorithm for programming the single-chip computer. We look through a series of sensors and will combine with modifications in accordance with lunar condition, and make our design in both hardware and software.